Hello and welcome to MT3. This is going to be a kind of an overview of some parts of ordinary differential equations. Uh, Now, I expect you to be looking at in parallel with what I've been doing, what I will be doing in this recording. Look at Riley, Hobson and Ben's chapters 14 and 15. Now, this particular recording will be focused mainly on chapter 14, that's on first order ordinary differential equations, but there will be a couple of ideas taken from chapter 15, which is on second order ODEs. Alright, so let's have a brief recap. So what ordinary differential equations are. They are equations of the form where you got some differential operator operating on some function y, and the kind we'll be looking at in this particular when we're looking at ordinary differential equations, we generally have one independent variable, and that will be x or time, so position or time, but it's one dimension. So the function y then is a function of x. Okay, and then typically, so you should recognize this equation. It's a simple harmonic oscillator equation. Now there are a couple of kind of properties of these ODEs which we use to classify them. The first is the order. So the order in this for this particular ODE is its second order. It's the order is 2, and the order is the highest derivative in the equation. In this case, it's the second derivative. Now the degree is the power to which the highest derivative is raised, and in this case, the second derivative is raised to the power of 1. So it's of degree 1, and this power is you decided on what the degree is after you have rationalized the equation. As an example in Riley, Hobson and Benz as to what they mean by this. This degree is not so important for what we are doing, so I won't say anything more. If you want to find out more, have a look in RH Riley, Hobson and Benz chapter 14. Okay, now the differential equations we'll be dealing with are those which are linear. So a linear differential equation satisfies, as you all know, it's a linear operator, satisfies the conditions for a linear operator. So if L is your differential operator, then L operating on the linear combination of functions y1 and y2, where a and b are constants, will be a times L operating on y1 plus b times L operating on y2. And these are the kinds of equations we're going to be using, but there's a lot of physics which involves nonlinear equations. For example, one of them is given here. It's a logistic equation which is used in population dynamics. And this particular equation involves the square of p. So p is t is time now is our independent variable. P is dependent on time, and we've got the square of p appearing on the right hand side. Now what this means then is that if you have two solutions, p1 of time and p2 of time, then the sum will generally not be a solution. Now yeah, this causes problems when you're trying to solve such an equation, but the physics is cool. I mean, you can get chaos, you can get solitons, there's all kinds of nice stuff happening in there. Anybody dealing with plasmas will be dealing with nonlinear differential equations. Anyone dealing with um, what happens when you have strong magnetic fields, as in the sun or as in kind of a star which is exploded. I mean, you will have nonlinearity in all these systems, but we won't be dealing with nonlinear systems except just briefly in this particular part of our course. Okay, now here's a concept which is taken from chapter 15 of Riley, Hobson and Benz. It's the idea of particular and complementary solutions. Let's just have a look. We'll see it again later. So if L is an operator operating on y, and this is equal to some f of x is sometimes called the source function. Alright, and let's say L is of order n. So that's the highest derivative in this operator. L is nth, it's the nth derivative. In order to get the complementary solutions, and these would be solutions in plural, it's a plural there, we solve the equation, what's called the homogeneous equation. L operates on y, and that gives you 0. So this is the homogeneous equation. And here what we've done is we've taken our source function and set it to 0. And this will give you a solution y of c which contains n unknown constants. Why n? Because it's a differential equation of order n. And as we'll see later on, there will always be, if the order is 1, then you will have one unknown constant. If the order is 2, you will have two unknown constants, and this carries on. Now, in order to get a particular solution, so this is the complementary solution, the particular solution is you find a solution, any solution to this equation. And therefore, these are not unique. Yeah? So let's call this y of p of x, and then the general solution will be the sum of these two. Now I'd like you to check to see that y defined like this is going to be a general solution to this equation. Why is it? First of all, check to see that it is a solution. Secondly, and this is something we will kind of prove later, it's a general solution because it has n unknown constants in it. And exactly why this makes it a general solution, just wait for a bit. Okay, now we're going to look at some of the important classes of first order differential equations, ordinary differential equations. One of them is of the form dy by dx is equal to f of x comma y. And now I know some of you will be wondering if this is a function of x and y. Are we now dealing with partial differential equations? No, we are still dealing with ordinary differential equations. Just that what we have over here will be a function of x and y, but y itself is just a function of x. We're going to solve for y in the end. Now this can also be written more generally in the form of a of x and y times dx plus b of x and y times dy is equal to 0. And the way you see it is if you transform this equation, the first one, into the form f of x comma y times dx minus dy is equal to 0. That's just the rewriting of the first equation. Then you can recognize that if I set a to be f of x and b to be minus 1, I get the second form. And the second form is the more general form, but just recognize it's related to the first form. Now, if the second form, and now we come to Riley, Hobson and Ben's 14.2.2, where we deal with exact first order differential equations of this form. What they showed there is that if you have this particular relationship between the derivatives of a and b, so now it's the partial derivative of a with respect to y. Remember, a is the function which multiplies the dx. We are taking the partial of a with respect to y, and then if that is equal to the partial of b with respect to x, then this equation is said to be exact. And what that means is that there exists some function u of x and y such that du, I just take the total differential of u, du is equal to the partial of u with respect to x times dx plus the partial of u with respect to y times dy. Well, that will be equal to this equation. So it will be equal to a times dx plus b times dy, and that's equal to 0. Why is it 0? Because this combination is given to be 0. And that lets us identify that du by dx is equal to a and du by dy is equal to b. Okay. And when we can then integrate these differential equations, so if you integrate du by dx, we integrate it with respect to x. Du by and what we end up with then is that u of x and y is equal to the integral of a with respect to x, and then normally we'd have a constant. But in this particular case, because we're integrating with respect to one of the variables, the constant is not a constant really, it's just a constant with respect to x. So in general it could be a function of y, because if I'm integrating with respect to one of the variables, then it's as if we are considering the other variables fixed or constants. So this thing is not just the number c, it's going to be, it can be a function of y. Okay, and that's quite important. And in order to find this function of y, what you can do is take this equation for u of x comma y and insert it back into the second of the equations which we've got. So put it back into the partial of u with respect to y is equal to b, and that will help you identify what f is. Now there's an example in Riley, Hobson and Benz. I'd like you to have a look at this example and try and solve it. It's worked off fully there, so I will not say anything more here. I want you to actually try and follow those derivations. Okay. Uh, Now, it's rare to find exact equations. More often than not, you will have inexact equations. Now, here I have just written down a summary of what you will find in 14.2.3 in Riley, Hobson and Benz. So, a differential equation of the form given here, of this form a times dx plus b times dy is equal to 0, this is said to be inexact if the partial of a with respect to y is not equal to the partial of b with respect to x. Now here what we do is, and once again the details are provided in the book, we introduce an integrating factor mu of x and y. And the idea here is that we choose mu to make our differential equation exact. So if we multiply our differential equation by mu, so we'll have a mu times a dx plus mu times b dy, then the idea is that this function, you could call it a prime, so you could call this a prime dx plus b prime dy is equal to 0. Then the idea is that this equation is going to be exact. Okay, now the entire proof of how this works is in Riley's book, so I'm not going to go over it over here. Actually, I do go over it, but let me just summarize the main results before we do anything further. Riley concludes that the general problem of finding mu as a function of x and y is difficult. Instead, what we can do is to assume that mu is either a function of x only or a function of y only. Now, this may not work, but we can always try it. Now, if mu is a function of x only, then it can be shown, and this is where you look at the book, that mu of x will be given by the exponential of the integral of f of x dx, where f of x is 1 over b times the partial of a with respect to y minus the partial of b with respect to x. And if mu is equal to, mu is a function of y, then, in fact, we will show this here, that mu of y is given by the exponential of the integral of a function g of y dy, where g of y is given as by 1 over a times the partial of b with respect to x minus the partial of a with respect to y. So let's see how the second case arises over here. So here's the proof for the case where our ansatz is that mu is a function of y only. Alright, so this is an ansatz. Now, as I said before, this may not be true, and we need to find out when do we know if these ansatz, I don't know what's the plural of ansatz, but anyhow, we need to know when our ansatz will be true or false, but we'll come to that. So here's the idea then. We're going to be choosing mu such that our differential equation, which is multiplied by mu, becomes exact. And that means the partial of a prime, now a prime is mu times a, the partial of a prime with respect to y will be equal to the partial of b prime with respect to x. That's what I've written down here. So the partial of mu times a with respect to y is equal to the partial of mu times b with respect to x. And this is our requirement. Now we know that mu is a function of y only. So when you differentiate the left-hand side, what we end up with is just apply the chain rule, mu times the partial of a with respect to y, plus a times the total derivative of mu with respect to y. Now I put a question here, why do we get the total derivative here, not the partial? Well, mu is a function of y only, so the partial of, so the answer here would be the partial of mu with respect to y is equal to the total of mu with respect to y, since mu is a function of y. Okay, it doesn't have a second dependence. Mu does not depend on x, and that's why this becomes a total derivative. And on the other side, on the right hand side, since mu is independent of x, the partial with respect to x doesn't operate on mu, it operates only on b. So we get mu times the partial of b with respect to x. Now it may be that you need to brush up on how partial differentials operate. Uh, if you have followed this, then all good. If you are still a little bit stuck, go back to where you learned about partial differential equations. It's covered in Riley, Hobson, and Benz, and revise the relevant parts there. Or just ask me if you can't, if you still have difficulties. All right. So now we have the total derivative of mu with respect to y. Now I've just rearranged these terms, is equal to mu over a times the partial of b with respect to x minus the partial of a with respect to y. Okay. Now this is the function. So if we define g of y as 1 over a times this difference in the partials, then you can solve this, and I'd like you to show this. So I'm going to put a question there. Show this. You can solve this to show that mu itself is given by the exponential of the integral of g of y dy. Okay, and once you've got mu, what do you do then? Well, in principle, once you've got mu, you just multiply your differential equation by mu, and it becomes exact. And once it's exact, you can go back to the previous case where we have learned how to solve an exact equation, and you can use the technology we've got from here to find the solution. All right. I mean, this is something which is best you really have to try it out. Just make this thing exact, find the integrating factor, and this is an example from Riley's book, so you'll find a solution there. Now, here's a question which you really need to understand and answer before you use one of these integrating factors. It's how do we know if mu is a function of x or a function of y? Well, what we've been told is that if mu is a function of x, let's go back here to our little summary. If mu is a function of x, then mu is defined to be the exponential of the integral of f of x dx, and f of x is defined as this term. So if this function f, I'm just going to call it f for now, is indeed a function only of x, then only is mu a function of x. Likewise, if g is defined to be this bit here, 1 over a times the partial of b with respect to x minus the partial of a with respect to y, then if g turns out to be a function of y only, then only is this ansatz correct, that mu is a function of y only. So this is what I've summarized here. All right, so if mu is a function of x only, then f defined to be this thing here is a function of x only. And vice versa, what you should do then is just simply compute this term, and if it turns out to be a function of x, then we know that mu is a function of x. Likewise, if you compute this term here and it turns out to be a function of y only, then we know that mu is a function of y only. So what you need to do is work a little bit backwards. You start from here, find out which of these is a function of x or y, and then you know which integrating factor you're going to be using. Okay, let's move on. So we look at examples when we meet in the live sessions, but now I'm going to move on. I expect you to actually go back to Riley's book and work through the examples yourself and then compare it to what they have done in the book. Now we move on to linear equations. In linear equations, this is now Riley, Hobson, and Benz 14.2.4. Linear equations are found quite often, and they are of the form dy by dx plus some function p of x times y is equal to some function q of x. Now you can see that this again is a special case of the differential equations we've got above. You can rewrite this equation, I won't go into the details here, into the form a dx plus b dy is equal to 0. But the reason why we treat it as a special case is because they occur quite often in this particular form. Okay. Now once again here we are going to show that there exists, so you're going to suppose actually that there exists some integrating factor mu of x which allows us to do the following. If we multiply our differential equation by mu of x, then we get it into a particular form. So here's what the form is. So we're going to multiply throughout by mu of x. So mu of x times q, abrupt the right hand side onto the left hand side here. That will be mu of x times dy by dx plus mu of x times p of x y. And this is our ansatz. We're going to choose this mu of x such that this happens. Okay? So choose such that we get a total derivative. There. Now if this happens, then we can now solve for mu of x, and here's how it's done. So this total derivative is equal to this term on the left hand side, mu of x times q of x. And I'd like you now to show that this can be integrated. All right. Now how do we do that? You integrate, well, I'm going to leave this for you. So you show this. It's quite a simple exercise in differentiation. Now what about the integrating factor itself? Now you've got a solution y as in terms of mu of x, but what is mu of x? How do you choose mu of x such that this actually happens? And to find out how to do this, what we do now is, so to find y, I chose this part and this part, and we equated those two. To find out what how to find mu of x, we're going to choose the second part is and the last part, so the second and third parts, and equate them. So what we have here is mu times dy by dx plus mu times p times y. That's the second term, and that's equal to the last term. And the last term, if you differentiate using the chain rule, you will get mu times dy by dx plus y times d mu by dx. Now we've got a common term on both sides, so we can effectively cancel those and write down a simple differential equation for mu. D mu by dx is equal to y, mu times the function p, and that allows us to integrate this to get mu is equal to the exponential of the integral of p of x dx. Put that mu of x in our expression for y, and you've got the solution there. That's how this kind of a solution works. And here's an example as to how we are going to actually handle something like this. In this particular case, example, you've got a mass m, which is under free fall in an atmosphere. So there's mg acting on this mass. There's a drag force, and the drag force is given by its opposite to the direction it's moving. So I've called it minus beta times the velocity. Beta here is the drag coefficient. So you write down Newton's law, mass times acceleration is equal to mass times dv by dt, and that's equal to mg acting downwards minus the force acting upwards, sorry, plus the force acting upwards, which is minus beta times v, and this is what you've got there. Okay, rearrange this a little bit, and what you have is the derivative of the velocity with respect to time plus beta over m times the velocity is equal to g, and g is a constant, obviously. Now if you compare it to the form we had above, which is here, then we can see that our independent variable is not position anymore, it's time. Everything is a function of time. And our function p of x is now p of t. It's just a constant beta time over m. And q is another constant, which is equal to g. So we use our equations. We can write down our solution. The velocity as a function of time will be 1 over mu times the integral of mu times q dt, and the integrating factor mu is given by the exponential of the integral of p of t dt. Okay, let's find the integrating factor first. P itself is just beta over m, so mu becomes the exponential of the integral of beta over m dt, which is the exponential of beta times time over m. Now I put a question here, should we have included an integration constant? Because normally what happens is, if you integrate something like this, I'm going to choose a different color here. So normally the integral of beta over m dt would be written as beta t over m, which is what I've got there, plus some constant c. So what about this? Do we need it? Now, before I actually give you the answer, think about it. Do we actually need that constant c? If I put that constant c in there, what would happen to mu? Think about that. The answer is we don't need it. But I'd like you to understand why we don't need it. So actually put that c in there and see what happens to mu. Does it really change, or are we simply scaling it? I hope you can guess what the answer is. So so let me put it another way. If mu is an integrating factor, then a constant k times mu is also an integrating factor. But does it matter what k is, really? Because we're multiplying the entire equation by mu. So if we multiply it by k mu, are we really doing anything new? Think about that and then try and formulate an answer to this question. All right, so now our solution then is given by this equation here. The velocity as a function of time is 1 over mu times the integral of mu times q integrated with respect to time. So the velocity as a function of time is the exponential of minus beta t over m times the integral of e to the beta t over m, that's mu, times g, which is q, with respect to time, integrate with respect to time. And now we get a constant when we do the integration. This constant is needed because it's a non-trivial constant. The previous one, I hope you have convinced yourself it is a trivial constant. It's not needed. And then the solution is of the form mg over beta plus c times the exponential of minus beta t over m. So our next question then is, how do we find out what this constant c is? For this, we need some boundary conditions. Now, so far I haven't provided any boundary conditions, but let's provide them now. So if the velocity at time t is equal to 0 is equal to some constant v0, then we can, in the above equation, put time t is equal to 0. So this would be the exponential will give you 1. And we'd have v0 is equal to mg over beta plus c. That lets us define what c is. C is v0 minus mg over beta. And therefore we write down the general form of this velocity as a function of time I've written it down here. Now we can ask another question. This is now doing a little bit of physics. It's always nice to do this. As time t tends to infinity, so in the very long time scale, this exponential goes to 0. So what we are left with then is, and so does this go to 0. So what we are left with then is that this velocity as t goes to infinity, it tends to mg divided by beta, and this is a constant. This is called the terminal velocity, and this is something you've known about, that a body falling through the atmosphere without any additional forces on it, on the gravity obviously, it will attain a constant velocity after long enough time, and this is the terminal velocity given by this particular expression. By the way, this is only valid, and we haven't really said this, if the body is not falling slowly enough. When things get a little bit faster, then the drag force is no longer linearly dependent on the velocity. It actually becomes quadratically dependent, but that's another story. Okay, now if you've understood that, oh yes, here's a little bit of a further analysis of what we have done. Remember, we defined the complementary and particular solutions. Well, let's have a look at what these are for this particular equation. Our solution y is given by 1 over the integrating factor mu times the integral of qx mu x dx plus our constant c. Now I made the constant c explicit. Remember, we included it up here. We got the constant c. I've kept it now explicit there so that we can see what's going on. Okay, and we know what mu is. It's the exponential of the integral of p of x dx. Now if we set this source function q, remember what the source function was? The source function is this function of x, which is on the right hand side. If we set that function q to be 0, then, as I said earlier, we should get the complementary solution. Now this is the first order differential equation, so this complementary solution will have one constant in it, one unknown constant. Now if you set q to be 0 in this solution here, what you see is that our solution, and this is our complementary solution, will be 1 over mu. Now mu is given by this, so 1 over mu is simply the exponential of minus the integral of p of x dx times the constant c. And this is the complementary solution, and it contains the one constant which needs to be determined. What about the particular solution? Where is it? Well, to find the particular solution, I just find any solution to this equation, and it won't have a constant in it this time. So if I remove the constant from here, what we get is a particular solution, which is 1 over mu of x times the integral of q of x mu of x dx. This has no constant in it. And it depends on the source function. That's important. And the sum of these two gives us our general form for y. And this is something we're going to be seeing again and again as we write down these general solutions. You will find that they will contain a complementary solution and a particular solution. Sometimes you need to dig to find out where they are, but they will be there. Okay, I'm going to end here and leave you with a problem to solve. Here's the problem. You have an LR circuit, and I hope you remember your Kirchhoff laws. You can show quite easily, and if you have forgotten this, then please go back to your Kirchhoff's laws and show that you can write a differential equation for the current flowing in the circuit as L times di by dt plus Ri is equal to v of t, where this is the voltage, which is in general a function of time. I would like you to solve for the current I in terms of this voltage t, v of t, and then show that if this voltage was a constant, just v naught, that the current I is given by I naught plus a constant c times an exponential, where I naught is v naught over r. And then if you use the initial condition that the current at time t is equal to 0 over 0, find an expression for I as a function of time and show that it tends to a constant as time tends to infinity. And I'd like you to interpret that solution the way you did it when you learned this in the first place. Okay, so that's the question I'm going to leave you with. And with that, we have finished our brief overview of ordinary differential equations of the first order. For more, please look at Riley's book, and there are different kinds of ODEs tackled there, and you can see how these techniques are used together with other techniques to solve these first order ODEs. Thanks for watching.